Hello there. Welcome to the Learning of Engineering video lectures. So in this video lectures, we are trying to learn how much amount of the strain energy stored in a shaft due to the torsional loads. As we know, the strain energy mainly is developing due to the straining effect of that body, and that too within the elastic limit. If the crossing the elastic limit, that energy is releasing to deform the material into the completely in the plastic level. So the plastic deformation will going to be occur. So whatever the magnitude we are going to be calculating here, the strain energy, and that is in the shaft due to the torsional loads. As we know, when the member is going to be subjected to the tensile force, then what happens? It will going to be start to elongate. Once you release the load, and this stretching effect will going to be comes to the normal position. It means that body is absorbing some energy while you are applying the forces. And similarly, it is using to come back its original position. That is called inherent forces are going to be acting. So in this case, that load is going to be coming in form of the torsional loads. That means here the torque is going to be acting on that system. Suppose this is going to be representing the shaft of the system, and the T is going to be acting. In this case, what happened? The two equal and opposite forces are going to be acting on that system. So then the torque is going to be generating. In this case also, when the member is going to be taught to twist in this direction, so a little deformation or stretching is occur along the 360 degrees direction. And that will going to be helpful to regain its original position within the elastic limit. Now we need to find out the strain energy in a shaft. So for this one, as we know, when the member is going to be subjected to, so tensile forces that I have taken, the strain energy is equal to sigma square by the 2E into volume we have taken. So this is the equation we are borrowed from the strain energy in the previous videos. So then I am going to be using this one. This is the strain is going, that is the stresses are developed, Young's modulus and volume of the body. In this case, it is initially we are taking the elemental strip. So this elemental strip is going to be considering over here. That's going to be, this is going to be your elemental strip. In this elemental strip is going to be located at a distance of small r and having a thickness of dr, and the total radius is going to be the capital R. Now I am trying to find out the strain energy within this elemental strip. Then how could I am going to be writing this equation? So that is going to be U is equal to, in this case, this is the stresses are developed due to the tensile forces, and in this case the stresses are going to be developing. We do have that governing equation. What is that the governing equations? That's going to be the tau by r is equal to, this is going to be q by small r. This is the governing equation we do have, that is the c theta by L. So from this one I am using this governing equation. So in this case what will happen? This Q is going to be the shear stress are going to be developing. That's going to be the Q square. This is the stress developed due to the tensile load, and this is the stresses developed due to the torsional loads, divided by 2 into E is going to be the Young's modulus that's widely using for the tensile and compressive forces. But when there is a torsional loads are there, then we are using the modulus of rigidity, that is the C we are using here, 2C, and here is the volume is equal to the dV I am going to be considering here. Because that elemental strip, how much amount of energy it is conserved, we are determining. So in this case, we need to find out what is the Q and what is the dV, right? That Q I am going to be writing in terms of, the Q is nothing but, suppose this is for the elemental strip. I want to find out the total shaft, how much amount of the strain energy it is absorbed and it is retained in the process. So that Q is equal to the tau by r into small r. And this magnitude I got it for the shear stress. This is the amount, the magnitude it is going to be stored inside the system. And next, dV is equal to, how should you write? The dV is equal to, I am going to be writing dA into the length I am going to be considering. That is the length of the shaft into the elemental area. We know that elemental area is going to be, that's going to be 2 pi r into dr into L, we will get it. Right? This is the elemental strip we are going to be getting. So once I am getting the Q and the du, then I am going to be substituting in this equation to find out the total strain energy inside the system. Now we are substituting in this equation, that is the strain energy, that's Q is equal to tau by capital R into small r whole square divided by 2 into shear modulus and the dV is nothing but your, I am not writing this part, I am going to be taking this is directly, so that's going to be dA into L. We know the dA is the elemental area we have taken, then we will take the integration of that and then we will get it that part. So then after this one, what is the variable in this case? The radius is the variable, that's why it's varying from 0 to capital R. So further simplification of this equation, tau square R square capital R square into 2 into C dA into L. And further simplification I am going to be taking here, what are the constant parameters we are going to be and what are the variable parameters. So that means capital R, C, tau and L are going to be the constant parameters. So tau square L and 2C into R square and then R square dA we will get it. Then what I am going to do, I am taking the integration for that part. So that integration 0 to R, I am going to be considering this is the U. And further simplification, we know that R square dA is nothing but your polar moment of inertia. So that U is equal to, I am going to be considering the tau square L by 2C R square J I am going to be getting. Now in this case, the tau is going to be the shear stress, right, that is acted on the outer surface of your shaft, and L is going to be the length of the member, and C is the modulus of rigidity, and R is equal to, that's going to be your outer radius, that's R is equal to, I can say a D by 2, also I can write it for the solid shaft, and the hollow shaft we are going to be writing D0 minus D2 by D, that is D0 by 2 we can take it. And J is nothing but your polar moment of inertia, that's going to be J is equal to 5 by 32 into the D to the power of 4 we can take it. So if I am going to be substituting R as well as J in this equation, I can get that equation in terms of the total shear stress we are going to be getting. Now we are substituting in this equation, U is equal to tau square, L is going to be the constant, 2C R square, and we are going to be taking J is equal to 5 by 32 D to the power of 4. Now I can take it this as a reference, and the R is equal to D by 2 and the D is equal to 2R I can write it. So that is I am going to be writing here, that's going to be 2R whole to the power of 4 I am going to be getting. Alright, so then further simplification of this equation here, the tau square L 2C R square 5 by 32, that's going to be 2, 2, 4, 16 that I am going to be getting here, that is going to be 16 R to the power of 4 suppose. So from this equation once again we are going to be simplifying. So that means this is going to be how many times it will go? It's going to be the 2 times suppose, and R square will go here is going to be a single time. So then further simplification, the U is equal to, what is the value here? That's going to be tau square L 4C and then 5 R square. This L I am going to be writing over here. So pi R square L I can say that's going to be the volume of the object. So then once we are going to be having this equation, so I am going to be considering U is equal to tau square by 4C into the volume of the object. So this way I can calculate the strain energy stored in a shaft, that is the solid shaft, when it is subjected to the torsional loads. What we did it, what we learned from here. If you want to find out the strain energy in a shaft, first we have to take the elemental strip, and the reference we have taken when the member is going to be subjected to the tensile forces strain energy, that's going to be sigma square by 2E into volume, and then we have applied here is going to be the shear stresses and shear loads, and then the elemental strip we have converted into the total shaft, how much amount of the strain energy it is consuming means this is the amount it is going to be consuming. I hope you are able to understand the concept, how to develop the mathematical model, and from this one if you substitute any numerical values so that we can get it the strain energy stored within the body. So this is going to be helpful to design of a shaft, and further analysis and the synthesis also going to be helpful to you. So thank you. I hope you are able to understand. If still you feel any difficulty or any confusion, just put in the comment section so that I can reach you out. Thank you.